Good morning. My name is David Emberson, and I am in the HPC AI Advanced Development Group in Hewlett-Packard Enterprise. My primary research interest over the years, the last few years, has been memory architectures. And so I've been a principal investigator for a program there that's been running since about 2017, and is really could be viewed as a successor to the machine project for those of you who know about the machine. And I'll talk a little bit about that. My main purpose here today is to set the stage for Clarette Crosta, who is actually doing some of the implementation work and architecture on a caching system, which she'll talk about. I guess, let's see, what button do I hit? This one? How do I make the slide go? Oh, no? Yeah, oh, down, okay. Down we go, there we go. Okay, so there's a couple of slides here we have that are based on market research data and some of the IDC stuff. And you've all seen this before about the exponential growth in storage requirements and the amount of data being produced, which is doubling pretty much every year. And that's really the argument for the growth in the storage market. I really want to talk about something a little different, which is more like the previous speaker was talking about, which is how to store things and what the problems are at the high end of HPC. So, the customers that I deal with are largely customers who are doing very large, high-performance computing systems, Oak Ridge, Los Alamos, Department of Defense, Livermore, and Europeans and Asian customers as well. And these are very large systems, generally sometimes, well, usually $50 million and up, and sometimes much more than that. So huge installations, and so the notion of storage has become a big issue on these systems for performance reasons. Recently, HPE invested in the Deos team. The Deos team moved from Intel to HPE, and we're making big investments in that team and working on successors to the cluster store system, the Cray cluster store system. So some of the work that we're doing in advanced development in collaboration with HP Labs is really looking a little bit farther out along that product vector. So something that we hope will work well at the high end of the storage space, but also can help people at the lower tiers of HPC. I mean, there's no such thing as an inexpensive HPC, right? But the edge systems for AI, for example, and the AI large language models and workloads companies like OpenAI and Google that offer interactive services. These are kind of a new frontier for HPC systems, which in the past have been largely batch systems. So we have this notion of interactivity, and we also have the problem of the computation that we're doing. And so I want to talk about that a little bit and about memory-driven computing before I turn it over to Clarette. I was told about a book called Graph Analytics in the Language of Linear Algebra. And I forget the author's name, but the person who referred this book to me was mathematician at the Defense Department. And I got a copy of the book and read it, and it was a collection of papers by leading researchers in the graph analytics field, explaining their algorithms in terms of linear algebra. And then I got to the end of the book, and it says, future research, we need to do more work on parallel algorithms and parallel storage systems. And it's like, well, okay, so we're all at this place now where we're really trying to figure out how to factor these problems to optimize their performance and get the data close to the computation. So now we have two big problems in HPC. One is data movement, and the other one is energy consumption. And they are not unrelated. Moving data actually in a supercomputer takes about 30 to 35% of the wall plug power. So just moving bits around in the machine. And this is because we're running a very high performance multi-dimensional network, and we have to transmit bits rapidly from point A to point B, and sometimes we have to do that in things like broadcasts and other kind of algorithms like scatter-gather and data reduction algorithms, which you're all familiar with. I want to talk a little bit about fabric-attached memory, which was the focus of the machine project, and this really got started after the invention of the oxygen-based memristor in HP labs, which allowed the construction of non-volatile memory, at least in theory. And so there's various ways of doing this. That was one of the technologies. The technology called phase change memory was the technology that was used in Intel Optane, which was the only type of this memory that made it to productization. And unfortunately, it was a financial failure and never really made it past the second generation of silicon, so it never really met its promises. It had some technical problems as well. But the upshot of this was that it drove the idea of a new memory tier between storage and memory, which we called FAM, disaggregated memory, where we had memory servers connected to the network. And of course, in the beginning, HP, then HPE had their own interconnect design based on Gen Z, which had memory semantics. So the idea was that we would have this big shared memory pool, and the compute nodes could share data structures on that memory, and that the memory had non-volatility and was designed for certain resilience properties, and so you could store intermediate results between processes and so forth, and get that data in the network and out of the storage system, and hopefully have order of 200 to 300 microsecond access time to that memory. We actually implemented some of that in our prototypes. The one that I built for this program is really based on, it has 80 terabytes of Optane, but it also has a lot of DRAM, because one thing that we wanted to do was dial the performance of the DRAM and make it slower, faster, and see what effect that had on the performance of our algorithms. But in the end, what happened was we couldn't get the non-volatile components that we wanted to get, and so that technology is not dead, but it's the players that were doing research on it sort of lost interest in it after Intel lost several $1 billion. They kind of got out of the game, and if you look at what it takes to make a memory factory, it's probably minimum $25, $30 billion investment. And so the startup companies have a very difficult time talking somebody like Samsung or TSMC into allowing them to pour their magic goo into some machine on their fab lines. to run a few wafers. So that's one of the problems they have, and there are some promising technologies. I won't go off on that tangent, but I do think that will happen one day. But what's happening now is really happening in the DRAM space. I sit on 2 committees in JEDEC, 42.2, which is the HBM committee, and 42.6, which is the LPDDR committee. And so I think what you're going to see in memory technology coming up is, first of all, you have the 32 gigabit chips, and they're even talking about 42 gigabit and 64 gigabit in some cases. And there are design improvements to the HBM stacks so that those will go to 16 high. And also, you'll see custom base die, which can have controller functions and some compute functions, and also LPDDR interfaces. So the principal GPU vendors are actively looking at attaching LPDDR directly to the controller of HBM stacks. So you'll build in a 2-level memory tier on those HBM stacks for GPUs and vastly increase the amount of memory available per GPU, which is something that AI really wants. So those are technology trends that you need to be interested in. What I do want to say, to get back to the topic of linear algebra, is that a great number of problems can be reduced to the problem of dealing with sparse matrices. And so there's a lot of work going on into how to optimize sparse matrices storage for not only to minimize the size, but also to make it easy to access. If you look at a format like CSR format, for example, and you have a large data set, you have to transmit, trillions of data items around to all of the nodes in a cluster, and that is a very expensive operation. So that's not a very good format for parallel access, although it is one for minimizing the memory size. So you have to make a trade-off to increase the memory footprint of the matrix in order to partition it over a number of nodes. So what we have done as a result of the idea of having fabric-attached memory is our group designed an API for managing and accessing regions and data structures on fabric-attached memory. And Claret was central to that effort. So now we have this wonderful open FAM API, which allows us to share data structures in an organized way on a very large cluster and scale it up. What we don't have is Optane or something like Optane. So the logical thing to do is to move to DRAM-based memory nodes. And it turns out that if you start moving computation over to the memory nodes, those memory nodes start to look an awful lot like compute nodes. So it also pays to have a caching client on the compute node side. And some you may or may not have memory nodes at all. That's a total option. But you can still use this API to access enormous data structures that exceed the sum total of the memory in the supercomputer. So for example, if I have a system like Livermore, where I've got, I don't know what it is, 5-6 terabytes of memory, or excuse me, petabytes of memory in the system, and I have data structures that are 100 times that size, but sparse, I have to figure out how to make that so an application can directly address something that's that large, which means that you have to support 64-bit addressing or something on that order, 56 at least, and then you have to have a way of mapping that from your caching system to the storage system. In addition, Another issue that we have is reliability and having to deal with system MTBF. This is a huge problem in machine learning, as you know, and so a lot of discussion about checkpointing of large language models. And so one of the things that we want to do is we have some work that we've done in the past on resilient runtime. That's not really the subject of this talk, but if you have a non-volatile resilient tier and a way of using that to hold run queues and intermediate data between processes, then you can build a runtime that can do seamless failover. And so that's another aspect of our program. So what I'm going to do now is turn this over to Clarette and let her talk about the caching system, because I think that's most relevant to this audience. So, all right. Thank you.
Thank you, Dave, for the excellent background. And I'm happy to be here to take you over the details of the caching system. We've heard multiple times throughout the different sessions last few days that HPC and AI applications are generating and processing huge amounts of data, and they need results in near real time. And centralized storage can often become a bottleneck, and there are solutions that are being evaluated, and caching is at the forefront. There are two types of caching. We've heard about server-side caching and client-side caching. And client-side caching is particularly interesting because the client-side cache can scale when the compute nodes scale, because the caching is on the clients, and you can scale the cache when the compute nodes scale, both in terms of size as well as bandwidth. So the size is understood because when you scale the compute nodes, you are going to scale the cache size. The bandwidth also, because you now have increased aggregate bandwidth that is coming from the additional nodes that you're adding into the system. For this reason, HPE is looking at building an efficient global distributed caching system that can augment HPC file systems. And towards that effort, we have this architecture that I'm going to talk about, and I will outline a high-level architecture of our design, and I will go into a little bit detail about the main components of this caching system. We'll look at some of the results with PageRank and SPMV, and we will then have a look at what we have in plan for the future and conclude with the summary. Okay, so here is the architecture diagram for our caching system. And the way we are building this client-side cache is by pooling portions of memory contribution from the nodes on the cluster. So these nodes could be compute nodes or memory nodes. So the compute nodes, if they have additional memory to spare, they can contribute that memory to this pool. So it is not the design is flexible. It is not mandatory that every participating compute node contributes a portion of memory. If it has extra memory, if it has stranded memory, that memory can go into this pool contribution. Also, the amount of memory you can contribute, a compute node can contribute, is flexible. So any amount of memory that is available goes into this pool, and if there is not enough memory with the compute nodes, the system can be beefed up with some dedicated memory server nodes, which are just going to contribute memory to this memory pool. And the compute nodes themselves can be heterogeneous with just CPUs or GPUs and accelerators. And the other important aspect of this caching system that we are building is we are looking at it as a multi-tiered caching system. So apart from the DRAM contribution, the compute nodes can also contribute local SSD space, and the caching system uses this local SSD space as a spillover space for the cache to balance between performance and cost. And the other aspect of this caching system is the data management and data movement. Dave spoke about why data movement is so important and critical in large systems. And what we are enabling with this system is that we want to have the data where the processing is happening. And we want to have the compute closer to the data, and the cache manager that is managing this pool of memory has visibility into the data locality, and that data locality can be queried by frameworks like a scheduler or a runtime that we are again building, which Dave alluded to, and that can place the computation closer to the data wherever it resides. And the data also moves between the different tiers, like I mentioned, between currently SSDs and DRAM, with new memory types and other things being possible. We have designed to accommodate that in the future, but right now we are looking at DRAM and SSDs, the local connected SSDs. And more importantly, all these nodes in the system are connected using a high-speed interconnect like Slingshot, and that's important because the whole caching system relies on efficient data movement using RDMA over interconnects like Slingshot. So here we will look at a working model of what the caching system looks like. So we have the applications which use file systems, and there are file system operations that the application calls, and these file system operations are routed to the cache by the cache manager. There are ways in which we are accomplishing this. I do not want to get into the details of that, but the file system operations are routed to the cache, and once they are in the cache manager decides where to place them in terms of the nodes and in terms of the storage tiers, and the cache manager then commits these contents in the cache to the persistent store using the file system and object store APIs. And as I said, the cache manager is central to this design. It is one of the main components. The second main attribute is the RDMA framework that we are using here that allows us to take benefit of data that is residing on the client side. And we are using the OpenFAM framework again, and I'll talk about the details of the OpenFAM frameworks a little bit more in the subsequent slides. And the third main piece of this architecture is the cache manager API and configuration capabilities. So the cache manager provides a set of APIs using which the cache can be configured, and also APIs that the frameworks can use to control the cache attributes, and also to query data locality. Like I said, frameworks like runtimes can query data locality to be able to schedule compute closer to the data. So in this slide, we'll look a little more deeper into the cache manager features and the functionalities. So as I said, the cache manager is central to this design. It's a distributed cache manager, which means that the cache manager component is present on every node from which the applications access storage. So it is linked with the applications, and the cache manager maintains global metadata. So the cache manager has, across the nodes, the cache manager has knowledge about the entire pool of memory, and it tracks the different allocations within the cache. We call them segments. It tracks dirty pages, it tracks dirty segments, and it provides a set of configurable policies. To begin with, we are starting with things like FIFO and LRU, but we do understand that not all applications have the same requirements. So from the start, we are making the design configurable such that we can accommodate new and different caching policies as per application requirements. And The cache manager also manages data consistency. That is very important because this is a shared global cache and it is being accessed from the different compute nodes. So it requires algorithms and framework for ensuring data consistency and correctness. That's one of the primary aspects of and the functionalities of the cache manager. And as I said, the cache manager provides APIs and interfaces upwards, and then it calls the APIs, the file system, and the storage APIs to persist data from the cache into the storage tier. So I have a slide on the kind of APIs that we are thinking about right now that the cache manager provides. As I said, it is mainly to configure the cache efficiently for different workloads and also to help frameworks to better utilize the cache. And I have just listed a set of key APIs, and the object management APIs are similar to the file open and the file close APIs, where each file or object in the cache is identified by an object name, and there is an open object call, and that call returns a handle to the object, and any subsequent operations to that object use the handle. For example, the read and the write then use the handle. So all of this are not actually exposed to the application. The application is completely agnostic of the opens, the reads, and the writes, because all that the application is doing is file system accesses, and those are routed to the cache, and it is the components in between that end up calling these APIs. But I'm just listing it here for context because some of these can be utilized by the frameworks, for example, the locality information and other APIs. And the ones that are visible to the user are the get cache configuration and the set cache configuration kind of APIs, which allow you to define some of the properties of the cache depending on application requirements. So in this slide, I will introduce OpenFAM because that is the framework that we are using for efficient data access or efficient access of this pool of global memory or this pool of cache. So initially, we had built the OpenFAM API just as a reference implementation for accessing remote memory. And at that time, initially, it was focused on accessing non-volatile memory. But then we did not have anything specific in OpenFAM that restricted it from accessing remote memory, which is not non-volatile. So we are able to leverage that framework for just accessing remote memory and using the RDMA capability there. And the OpenFAM architecture is based on a client and server architecture. The client runs on the compute nodes from where the remote memory accesses are to be made, and the server component runs on the nodes that is contributing memory to this pool or the fabric attached memory pool. And so what you can see in the cluster that I just explained in the architecture slide is there are some nodes which are just acting as memory server nodes. So in those cases, you will just have the memory node component present on those memory servers. But in the cases where you have a compute node which is running applications and as well as contributing memory, you will have both the compute stack, the OpenFAM client stack and the server stack co-located on the same node. So because it is accessing the memory as well as giving some memory to the memory pool, so you need these two different stacks to be running on that node. And the compute node itself, the client itself has, like I said, the application and linked with OpenFAM client, the library, the API calls, and then there is an RPC client which allows you to do data path operations like allocating space in the memory. So you initiate that from the client, it goes as an RPC operation to the server, and the server receives that operation and allocates the required space in memory and returns back handles which can later be used for data access. And all of this go through libfabric, We use the corresponding provider depending on the network that we are using for slingshot, InfiniBand, etc. And similarly, on the memory side, you have the RPC server, which receives the control path calls, and you have a memory manager component that controls the memory portion that is being contributed by that specific node. So this memory manager component just has visibility to the memory contribution from the node on which it is running. It is the cache manager component that works on top of it that has knowledge of all of the memory contributions that are coming across the nodes. So we are utilizing this base framework, and we are building a cache manager on top of this. And we are having the cache manager do all of this work, calling the OpenFAM APIs for data movement, for data access, and controlling and allocating contents on the memory nodes. And it is all something that the cache manager internally handles. So a little bit more about the background of OpenFAM API, just to understand it a little better. It was basically inspired by OpenSHMEM. So if you're aware of distributed parallel programming models, OpenSHMEM is one of them. And the OpenFAM API is inspired by OpenSHMEM and a lot of the work that went into the machine program that Dave was leading. So if the API looks very close and very similar to the OpenSHMEM API, but there are a lot of differences too. While the API looks similar, the functionality is not. And the reason for that is we have good reasons for doing that. In OpenSHMEM, whenever there's a portion of memory that is being allocated, OpenSHMEM requires all participating compute nodes to allocate the same amount of memory. So it is symmetric. And it is mandatory that each and every node allocates the same amount of memory, whether it is used or not. And also that portion of memory is tied with that PE in the sense that if another PE, when I say PE, it is a processing entity. You can think of it as the compute node on which the applications are running. So when there is another PE that wants to access the remote PE's memory, it has to always direct it to that particular PE from where it wants to access. But the way we have designed fabric attached memory, it is a central pool. The memory allocation is not tied to any particular PE, and any compute node can access this portion of memory, whether or not they are contributing to it. So there is no mandate that there has to be a contribution and it has to be symmetric. And also, because of the fact that it is not associated with any PE, the content in FAM can outlive the application life cycle. So it is available for other applications to use to. It is available for other applications to take benefit from the contents in FAM. So that's how the OpenFAM API differentiates itself from the OpenSHMEM API, and all this groundwork is good because it is these basic principles that is allowing us to use OpenFAM as the backend framework for building our caching system. This again is just listing the kind of APIs that OpenFAM provides for the RDMA operations. You have the gets, the puts, blocking, non-blocking operations, gather, scatters, atomic operations, memory ordering and collective operations, and as I mentioned, the data path operations, which are the memory management operations like region and data item creation. So regions and data items are the units of allocation, as we call them, for fabric attached memory. So OpenFAM provides the memory management operations to be able to allocate and manage these. So the performance of OpenFAM is important because that in a way tells what the cache performance is going to be. Although there's additional overhead that is coming from the cache because of the additional metadata that the cache is maintaining and other things. But at the base, what we have is the OpenFAM RDMA access cost, and I have some latency and bandwidth numbers for this. If you see this slide, we are looking at small message accesses, and for the message sizes of 8 bytes to 256 bytes, what we see is we have a latency of less than 5 microseconds for the RDMA access. As I said, this is going to be the base for our caching functionality, although it is not going to be less than 5 microseconds because there is going to be overhead with the other metadata and other operations the cache manager has to take care of, but this is fundamental to what we can rely on for the performance of the cache. Here we have the bandwidth numbers. Again, all of these experiments are run on the system that Dave spoke about that we built with 52 nodes with a lot of Optane but with a lot of memory too. So all the experiments are run on the same node, the same cluster. And here we have the results of the throughput, and we have message sizes ranging from all the way from 64 to, I think, 4M. We have, in this experiment, we just have one processing entity accessing data from a remote memory server, from a single remote memory server. And the processing entity is configured with different number of threads. And what we see is higher the number of threads, you're able to achieve link bandwidth with smaller sizes. So for example, you are able to achieve link bandwidth of 25 Gbps with 8 threads for about 2K page size. And I think for one thread, I think it is about 8K page size. So ultimately, with the different transfer sizes, we are able to achieve link bandwidth, and that's the throughput numbers that we have here with OpenFAM. Switching gears a little bit from OpenFAM and back to what we have built using OpenFAM, that is the caching system. I'm going to talk about a little bit about the application that we are using to measure what we can expect with our caching system, and that is PageRank. You may be well aware what PageRank is. It's a web page ranking algorithm developed by Google, named after its founder, Larry Page. Here the web is represented as a directed graph where nodes are the web pages and edges are the hyperlinks. And the score for a page, or the importance for the page, is determined by the quality and quantity of incoming links. And the way the page rank or the score for a page is determined is by using iterative SPMV. Again, Dave mentioned SPMV is at the core of a lot of frameworks and workloads. So iterative SPMV is what is used for PageRank. And in the SPMV representation, the web graph is represented as a sparse matrix, where each row in the matrix is a web page and each entry is a hyperlink. And the vector, which is used for multiplication, is the rank scores of each page. And the input matrix and the vector are multiplied using the SPMV operation, and you get the updated page vector, which is basically the updated score for each of the web pages. So, and then this process is repeated until the results converge. So what we are doing with this to demonstrate the benefit of the cache is that we are using a baseline measurement where we have PageRank, which is multiple iterations of SPMV. For simplicity, I am just using 3 workers, and each iteration of SPMV is split into 3 tasks. So one iteration is 3 tasks, and is distributed across 3 workers. And then the iteration repeats. What happens in the baseline version is that there is no knowledge of the tasks that are already being scheduled in the first iteration. So it's a random set of new tasks that is scheduled on every iteration. And what we have in this fabric attached memory is the input matrix and the input vector. So every time you are doing the SPMV operation, for each task, the input matrix is fetched from remote memory. Again, we are using the remote memory and the cache that is there, the client-side cache within the node, just as a representation. We could extend this to external storage. So in the place of remote memory, we could have external storage. But just to demonstrate the benefits of locality-aware scheduling, we are looking at this model where we have all of the data already read into remote memory, that is the FAM pool, and then the workers are reading the necessary pieces from this remote memory. And you see, because the tasks are different across every iteration, the portions of the input matrix are different, and every time the worker is ending up reading the matrix from the remote memory. But in the optimized version with our caching system, what we have is that once the input matrix is read for the first iteration, we save it in the local cache, and also we have a scheduler that is aware of this placement, data placement, and we schedule operations in such a way that the same worker gets the same operation in the next SPMV iteration. So that way, the second iteration just makes use of the locally available portion of the input matrix, and because of that, the subsequent accesses do not have to go back to remote memory. Again, for simplicity, I am just showing 2 iterations, but in reality, there will be multiple iterations of this SPMV operation. So that was the background for the experiment. Now let's look at some of the results. So we had a matrix size, a sparse matrix size of 16M by 16M, and we had 16 workers in our configuration, in our test setup, and we had the remote memory contribution coming from 4 different memory servers, or the memory nodes. All of them were connected over slingshots. Again, it's the same system that we used for the FAM experiments too. And what we see for one iteration of PageRank with and without the client cache and the locality-aware scheduling is that the time taken is similar because it's the same accesses and it is the same computation. But for subsequent iterations, the time taken by the locality-aware PageRank version is much lesser, and with 8 iteration, the PageRank algorithm is almost close to 7x faster. This also indicates that PageRank is memory bound. And the inference here is that frameworks like the runtime can really take advantage of the caching system because it is one thing to have the data in the cache, it's another thing to utilize it efficiently. So that is where our the runtime system that we are building is important. Apart from providing resilience, we are also looking at it to optimally use the cache that we are building for the system. So with that, some of the things that we want to do with this caching system is, as I mentioned, we want to provide multiple configurable caching policies so that we cater to different workloads. Similarly, for the invalidation mechanisms as well. And this wouldn't go anywhere if we did not have an efficient integration with the GPUs. So we need to enable the GPUs to access this cache efficiently, and that is something that we want to build with our caching system, and also focusing on the runtime framework that can take advantage of the cache. There are things that we want to do in the long term, like dynamic capacity adjustments of the cache, and expand support to other HPC file systems. So going back to what Dave mentioned, today we are targeting this cache for DAOs, the Distributed Asynchronous Object Store, which is a hexascale storage system recently acquired by HPE. So the cache that we are working with the DAOs team to integrate this cache into and augment DAOs with this cache for performance benefits. Once we have completed this validation phase and we have demonstrated performance, we want to take this to other HPC file systems like Lustre, and we also believe that the server-side caching can also be extended with the concept of FAM, but I'm not going to get into the detail of that, but we will look at it when we have to do it, and that requires validation. So in conclusion, we are proposing a solution that can take advantage of the standard memory or additional memory that the compute nodes have, and be able to create this pool of cache. And we want to support heterogeneous compute with the intention of reducing the latency and improving efficiency of accesses to the storage systems. And the important part here is that I think the key value proposition is that the client-side caching can scale when the compute scales, both in terms of size and bandwidth. We are enabling the cache to work with diverse workloads, and we want to extend this to additional file systems and optimize it for emerging workloads. So I think that is about what I had to talk about in the session. I have a few acknowledgements because we are working with different people within the organization, with the DEOS team, with the IDS team. IDS is an application within HPE. We are trying to showcase or demonstrate the benefit of cache with that. We are also working with different frameworks like Arcoda and Chapel, and seeing if that is something that we can extend to. And I would like to hear any feedback that you all may have about any workloads or data that can benefit from a solution like this. And if you have any questions, I think we are open to questions. Dave and I are open to questions now. We do have, I think, 4 minutes. Yeah.
So, really nice talk and exciting work. So I'm wondering how mature is OpenFAM right now, like open source project?
Yes.
I have an application, I have different file system, GPFS, BGFS, and I'd like to try to add this the support of FAM to those applications or systems. Is it mature enough already for that, or yet?
Yeah, we do have an open source version of OpenFAM, which you can look up. It is available. You can try it out. We have tested it with Slingshot, and I think up to the latest version with InfiniBand. We have measured the performance numbers, and it is consistent with what I have shown here with the slides. But having said that, we don't have a support system. Dave, do you want to add anything more to this question on OpenFAM support or maturity?
Yeah, do you have the URL in your slides? It's
I
on
think
GitHub.
one of the slides does have it, but I could provide if.
Yeah, I would suggest going through that, and it's pretty well documented. And if you have questions, just send them to us, and depending on what you want to do, maybe collaborate. We're open to that.
Yeah.
And then maybe a follow-up, since you mentioned Slingshot and InfiniBand multiple times, and now when answering this question, do you think there is no perspective for this technology if it's a high throughput, low latency Ethernet, or it's like it limits the scope of performance so much that the use cases you're considering are no longer satisfied?
If you're just looking at OpenFAM, I think you will get what you get with the interconnects, because there is nothing that is working on top of it that is dependent on a specific performance requirement, right? So although we have not tested the latest versions with anything apart from these two things, I don't believe. I think even with that, you might just see the performance that you would expect with RDMA operations. I don't believe there is anything in the OpenFAM stack that restricts exploiting the maximum performance with anything else, any other interconnect. But we have just not tested it. You will need to have the right providers and the right interfaces underneath to be able to carry out the operations.
Yeah, so it pretty much runs atop libfabric. And so, if you have a lot of things that require the special hardware like collectives and sort of where there's acceleration capabilities beyond what Ethernet can do, or you have a large cluster that benefits from multidimensional, topologies of those networks, then yes, you're going to have performance limitations with Ethernet, but for experimental purposes, you're not going to see it on a small scale. And really, I think the direction that things are going, what's going to happen to Ethernet is Ultra Ethernet is happening. And so people are getting behind that. And the consortium has made great progress and released an initial specification. And I think they really need to get that into IEEE 802, as soon as possible. But that's really the technical direction that I think it's going to take. So I don't know what your horizon is or your interest, but
All right, so one is just development, like you said, and it sounds like you can use anything you want, right? But the second one is just fundamentally
right. Well, that's our domain. So we're looking 3 to 5 years out and trying to figure out where we want to be.
Yeah, we can probably talk a little bit more. Dave is going to be here for some more time, so yeah. Okay, but I think we've reached the end of the presentation. Thank you all. If there are more questions, we are available outside.